We're going to get into the first part of optics, actually the second part of optics, since we've already done some basic understanding of how light moves with lens and mirrors, and the things that you're going to be working with from an applications point of view are what? You're going to have the law of reflection, okay? The other side is going to be the law of refraction. So what are you going to get? This is going to be for lenses. This is going to be for mirrors. Okay? So this is where we're up to when it comes to optics. We're going to first start with these lenses, and we have what are called converging mirrors, and what are converging lenses and diverging lenses. Just like it sounds. Converge means the light comes together to a point. Diverge means the lens spreads out the light. Okay? This is going to be your convex. This is going to be your concave. Remember these words. I'm going to use them interchangeably. I'm assuming you know what's going on. Converging lens bring things to a focal point. Diverging lens spreads out that light. Okay? As far as things that we need to know, the parts of that convex lens, okay? Things that you need to be able to draw. You've got a principal axis. Okay? It's the axis straight through the center of the lens. You got a focal point. The point at which the ray of light, okay, passes through the axis and then through the lens. So you have, and for a lens you have focal points on both sides. And then you have a focal length, which is the distance between the focal point and the center of the lens. Okay? Okay, that's your focal length. So you got the principal axis straight through the center, the focal point, the point at which the rays of light come together, and then you have a focal length, which is the distance from the center of the lens to the focal points. Now, how do we construct these new images? Okay, if we don't have something to look through, we can do a lot of these graphically or mathematically on a page. We're going to do what's called a ray diagram, and this is a ray diagram down here, okay? It's a ray diagram. Notice you've got the principal axes, you've got focal points, you got the lens, and then here's your object. We standardize things, put the object on the left, we make it just an arrow, and we come off the tip of the arrow. So we are upright right here, okay? So the things that we need to look for, the size and location of the original object. Ask yourself, am I inside the focal point? Or am I outside the focal point? Okay, there's some assumptions you can go by when you start learning how to do this. If the object is outside of the focal point, certain things are going to happen. If the object is inside the focal point, certain things are going to happen. We can figure out where the new image is going to be, okay, without even having to take a picture or use this thing. Okay? Basically, they say here, think about a person standing at the end of the street. Well, this could be an object. Well, this could be a person. Okay? It doesn't matter. We're going to bring all the points off the top. Okay? The new image is what you actually see. We need 3 rays coming off the top of that arrow, or the top of your head, right, in order to intersect in order to intersect over on this side, right? That's going to be over here somewhere. Okay. This guy, the light comes off the top of his head from the left, ends up on the right. Okay, how are we going to do that? Well, maybe I can go to the next one. Why am not going here? Hold on. Here we go. We need to draw 3 rays to find the position to the right. There's 3 different ways. Think about it. Okay, and these are the same 3 rays no matter what you do. The first ray, parallel to the principal axis going in. Okay, parallel to the principal axis going in through the focal point, going out. That's number 1. Okay, parallel in through the focal point, out. We don't know where this is going to show up yet over here. We need 3 light rays to figure out where. Step 2, straight through the middle. Okay, if we go straight through the lens, we're actually not going to bend, and we're just going to keep on going on that way. Okay, the second ray, straight through the center of the lens. The third ray. Okay, again, we're starting at the top of this ray. This arrow, we're going through the focal point in, and then parallel out. Okay? 3 rays will define where you're going to be every time. Okay? Sorry, I was goofing around. No, I was just trying to see if we'd had them all in one spot. Remember, the first ray, parallel in through the focal point out. The second ray, straight through the center. The third ray, through the focal point in, parallel out. Those 3 rays will pinpoint where this image is going to be, and that's where it is. What do we notice about it? First off, is it right side up or upside down? Compared to our original one, we are, if you're on this side, you are inverted. Okay? The other thing that you have to look at is if we did this graphically and we did this correct, compare the size here versus the size here. We are smaller than when we started. Okay? So what do you think is going to happen when we get closer to the focal point? What do you think is going to happen to your image size? And sometimes you can think about it if you've ever had a magnifying glass or some type of a lens that you, when you get it closer to your eye, what's it doing? Okay? We get 2 different types of images in our business. We get a real image and we get a virtual image. Okay? A real image is formed when all the rays come from a single point on one side, converge to a single point on the other side. I can put a screen right here, and there will be an image there. Okay? These focal lines come together. This is real. We are inverted. Okay? This is real. This is inverted. Okay? Real images are where the rays converge, and you can actually put a screen there and see something. Virtual images are a little different. Virtual images occur when all of those lines don't come to a point. Okay? And how do we see that? A virtual image, I'm going to move this stuff off to the side. A virtual image forms when the light rays diverge through a lens, okay? Couple different ways. They're looking at them. This is actually a mirror right here, right? And if you're looking at yourself in a mirror, remember those ray lines are straight, okay? If you're looking at yourself in a mirror right here, right? You're looking at straight lines. You appear on the other side of the mirror. Do those lines ever come together and form an image? No, they do not. What else happens? Think about a situation down here. If you're inside the focal point on this second one, okay? Remember, the three rays we have, what are they going to be? Parallel in, through the focal point out, through the center of the lens. And what do we do with the other one, right? The other one is going to be through the focal point and then out. Well, you know that if these things come together over on this side, these guys aren't coming together over here, right? If your object is on the same side, this is your image here. It's going to be a virtual image. Okay? When you're inside the focal length, things get a little strange sometimes. Okay? If you have a diverging lens, right? If you have a diverging lens, these rays out here, they're going on, and they're all right. They're not going to come together. Okay? So you get virtual images with a diverging lens, or the object is inside the focal length on a converging lens. You also get it with mirrors, and I'll show you some of those in a minute. So try this. Well, they're trying to figure out, and this is one of those things that we just looked at. Remember, there's three rays you need. Parallel in, through the focal length out. That's number one. Number two, straight through the center of the lens. Are those puppies coming together? No, if they're coming together over here, right? So you would get a virtual image over on that side of the lens. You can't put a screen there and pick up an image. There's nothing there. Okay? There's something called the thin lens formula. This is the distance to the object, DO, distance to the image. Okay, this is the focal length. Okay? Use these in meters as well. Keeps our math a little straightforward. So we have 1 over the distance to the object plus 1 over distance to the image equals 1 over the focal length. Okay, remember, algebraically, this does not mean that DO plus DI equals F. Okay? Trying to see what else is here. The other thing, and we'll work some problems. I'll put up a video or so we can look at those problems. How do you see? Okay, I wear glasses. You guys know I can't see anything without my glasses on. All of y'all are all fuzzy. When we have nearsightedness, the eyeball is too long and the image focuses in front of the retina. Okay? We have farsightedness where it's too short. And I don't know that these images are as good as I would like, but, okay, if it focuses in front of the retina, right, if lines are coming in this way, right, your focal length is gonna be here, okay? If it's behind the retina, there's your incoming, right? Focus is behind the retina. You need a lens to pull that up a little bit. You need a lens here to push that image back a little bit. Okay? So if you wear glasses, there's a story about that. We'll talk a little more about that one too. Well, that looks like it's all for now. Again, we have an activity this week to have to deal with this math here. So we need to be able to do the math. Okay? We need to be able to do the math, and we need to be able to do some lens diagrams. Okay? We'll get your quizzes back to you on Monday as well, and let's take a look at those, and then we'll be all right. Thank you. Bye. Have a good week.